Okay, let's dive right into this explainer and follow the incredible high-stakes journey of a single API request navigating the modern web. Every time you open an app on your smartphone, whether you're ordering a ride, streaming a movie, or checking your bank balance, you're kicking off this fascinating process behind the scenes. Have you ever wondered how that data actually survives the incredibly complex, chaotic environment of modern backend architecture? Well, today we're going to break down exactly how it all comes together. To really grasp the massive scale of the problem we're looking at, consider this. By 2019, Uber's products were powered by over 2,200 individual microservices. 2,200. Just think about that for a second. When you tap a button to request a ride, you aren't just talking to one server. No way. Your single request triggers a massive cascade of thousands of independent systems handling routing, payments, notifications, you name it, and they all need to talk to each other simultaneously in real time. Operating at this massive scale introduces some pretty severe security and routing challenges. It's no longer just about keeping hackers out of one front door. It's about securing thousands of internal pathways. This is such a critical, mind-bending puzzle that it actually prompted official guidance from government agencies. NIST, for example, released Special Publication 800-204 purely to help organizations figure out how to secure these incredibly complex systems. So how exactly does data survive this maze? Here's our roadmap for today. We'll start with the microservices chaos. Then we'll compare gateways versus service meshes, look at controlling the traffic flow, explore the art of transformation, and finally we'll dive right into securing the edge layer. Starting off with Section 1, the microservices chaos. Let's take a look at the environment our data is stepping into. So in the old days, applications were monolithic, right? Just one giant block of code where fixing a simple typo could literally take down the whole server. But today, we've separated that monolith into tiny, loosely coupled, single-purpose microservices. And this fosters incredible agility and scalability. Your team can update the billing service without totally breaking the login service. But, and it's a big but, this architectural choice makes managing the communication between them incredibly complex. You're basically trading code complexity for network complexity, which requires some seriously advanced orchestration to keep everything running smoothly. Moving to Section 2, gateways versus service meshes. Let's meet the border patrol and the internal traffic cop that keep all this chaos organized. Think of the API gateway as the ambassador for your backend services. It acts as a centralized security checkpoint and the single entry point for all external clients, like mobile apps, web browsers, partner APIs, the whole shebang. Its primary job is to look at the incoming request and route it to the exact right microservice, all while enforcing strict security policies, so the outside world can't just access whatever it wants. But once inside that perimeter, the service mesh takes over. Unlike the centralized gateway, a service mesh utilizes a decentralized network of lightweight sidecar proxies. These proxies are deployed right alongside each individual microservice instance, and they automatically handle all that internal service-to-service communication. It's essentially the invisible fabric that allows, say, the billing service to securely find and talk to the notification service without needing any manual configuration. Now, what's really interesting here is how their roles sharply contrast. The gateway handles the outside world centrally, shielding the backend from the wild internet. Meanwhile, the service mesh secures the internal ecosystem in a completely decentralized way. They both offer fault tolerance, sure, but they apply it very differently. The key takeaway here is that they aren't competing technologies. They're actually a powerful combination working together to ensure your request reaches its destination safely. All right, Section 3, controlling the traffic flow. Let's see how these systems act like a bouncer to prevent catastrophic overloads. To prevent resource starvation from malicious DOS attacks, or honestly just unexpected viral traffic spikes, gateways use rate limiting. And a really brilliant way to visualize this is the token bucket algorithm, which is used by massive companies like Amazon and Stripe. Imagine a literal bucket with a set capacity. A refiller continuously drops tokens in at a steady rate. Every single incoming API request has to grab a token to proceed. But if traffic suddenly spikes and the bucket empties out, any new requests are simply dropped until more tokens arrive. It's just a super elegant way to allow brief bursts of traffic while still maintaining a strict overall speed limit. So if a rogue script or just a very impatient user hitting refresh exhausts those tokens, they're immediately hit with the infamous HTTP 429 status code. It means exactly what it says: too many requests. And what makes this so effective is that it's often accompanied by a retry after header. This explicitly tells the client exactly how many seconds to wait before trying again, preventing them from aggressively spamming the server and making the overload even worse. Next up, Section 4, the art of transformation. What happens when our API request doesn't actually speak the backend's language? Well, the API gateway steps in as an incredibly powerful on-the-fly translator. It modifies incoming requests so that legacy systems and modern APIs can communicate seamlessly. We call these the 3 pillars of request transformation. You've got header manipulation, which adds or removes tracking IDs. Then there's body transformation, which completely changes the data format. And finally, URL rewriting, which cleans up those public-facing links while routing to complex internal service paths. To put that into perspective, consider this before and after payload. Let's say the mobile client sends user and email, but the backend database was recently updated and now explicitly requires the terms username and email underscore address. Instead of forcing millions of users to download a brand new app update, which we know is a nightmare, the API gateway just intercepts the JSON payload, restructures the text, and even injects a brand new source tag. It ensures the payload exactly matches what the backend service expects, and it does it completely invisibly. Finally, Section 5. Securing the edge layer. Let's explore how we securely track our request across thousands of independent services. This is absolutely one of the hardest problems in distributed systems. At a massive scale, like Netflix serving 2.5 million requests per second, repeatedly decrypting complex external security tokens at every single microservice is going to completely bottleneck your system. Think about it. If a user presses play and that single request touches 50 internal services, forcing all 50 of them to independently decrypt and verify the original web token is a massive waste of computing power, and it introduces huge latency. But Netflix solved this beautifully by moving all authentication to their edge gateway. When a request arrives, the gateway validates and strips away those heavy external tokens, and it creates an internal passport. This passport is a short-lived, token-agnostic identity structure. It's essentially a highly secure, lightweight digital ID badge formatted as a protocol buffer and protected by a cryptographic hash. This badge is then passed down the chain, allowing internal microservices to simply read the passport instead of running those heavy decryption algorithms over and over again. And when you look at the performance data, you can clearly see how this builds an incredibly fast system. By centralizing authentication at the edge, Netflix dropped their relative latency from 100% down to 70%. That is a massive 30% reduction overall. Their API systems essentially became 30% faster overnight. They also saw huge drops in CPU load and memory usage across their entire backend fleet, simply because the microservices could finally focus purely on their business logic rather than security token decryption. And all of this leads to the ultimate payoff, the ability to seamlessly and securely serve 2.5 million highly authenticated requests every single second. When you combine a centralized API gateway handling transformations and edge authentication with a decentralized service mesh routing traffic and token buckets protecting the servers, you create an architecture that doesn't just survive microservices chaos, it absolutely thrives in it. So, as we wrap up this explainer, consider how these incredible tools could transform your own systems. Look at the architectural strategies we've covered today. Is your organization's architecture a resilient, streamlined mesh or a brittle monolith waiting to break under the pressure? Are you properly decoupling your edge security from your internal services? Ask yourself whether you are truly ready for millions of users. Keep learning, keep building, and we'll see you in the next explainer.